Welcome to this session of Shadow the Scientist. This is astronomy night with the LATIS and C3VO teams, hunting giants at the very edge of the universe. Again, I'm your host, Jamika Marshall. I'm the Shadow the Scientist Programs Manager. Now, the Shadow the Scientist initiative is brought to you by an amazing team at the University of California, Santa Cruz. Now, for this session, you are with an amazing group of astronomers. We have, as our science hosts, Dr. Brian Lemaux, Dr. Nima Chartab, Dr. Roy Gal, Dr. Ben Forrest, and Mr. Joel Diamond. Now, in this session, we have some exciting things going on. They're actually using, this is our very first time featuring the Magellan telescope at Las Campanas Observatory. And so I'm looking forward to hearing more about this telescope and why they're using it for their observations. I'd like to welcome Roy Gal, Dr. Roy Gal. Hi, thank you so much. And please get us started.
All right, aloha everyone. My name is Roy Gal. Mahalo, Jamaica. I'm actually sitting in Hawaii. So that's an example of our big international collaboration. We have astronomers from around the world in our actually two teams that are collaborating on this project, and we're using telescopes from all around the world. And this is actually my first time ever connecting with the Magellan telescope as well. They've used ones in Chile before, but not this one. So mahalo to Nima and their team for participating in this. So as a bit of background, as Jamika said, the science that we're working on, we'll hear a little bit more about that from the other people on the team. But just as a very broad background, what we're doing is we're trying to examine the largest large-scale structures in the early universe. You might have heard of galaxies. Galaxies tend to live together in cluster groups or big clusters of galaxies that might have hundreds or even thousands of galaxies in them. As we look back in time, those clusters are less structured. They're still building up, much in the same way as when we look at the planet, we didn't used to have mega cities like Tokyo and London and New York, but people were more scattered, but these cities built up over time. And we're actually looking back in time to an era early in the universe when these cities were still just collections of burbs. But the team that we're working with, rather than looking at where there are galaxies in the universe, has been looking at where there seems to be piles of gas in the universe. And usually those piles of gas form into galaxies. But they have found some structures where we're having a hard time seeing the galaxies. And right now, the observations that we're taking are designed to find those galaxies if they're there, but maybe acting a little bit weird. Because we expect that in all places in the universe, these piles of gas should just basically under gravity collapse and make galaxies. If that's not happening, then that's really interesting. If the kinds of galaxies that they're making are different in different places, that's also interesting. So we're really trying to figure out why these piles of gas seem to be lacking galaxies. So the way that we're doing that right now is using infrared light. We're looking for galaxies far away in the universe, and we're trying to identify them that they're at this same distance as the piles of gas. And the way that we're doing that, I'll talk about a little bit later, but I'll start out by talking about the fact that we're looking at infrared light. So that's light that has longer wavelengths than we normally see with our eyes. It's what cats can see. It has lower energy than visible light. And I'll have a couple of slides with some graphics so I will share my screen if that's okay, Jamika. So let's start with this picture. So I like to orient people to the concept that light exists in many more colors that we can see with our eyes. And I think some of the people here who are joining us, I've seen at others of our sessions, so they may know this very well. But I like to remind people that as humans and most animals, we're extremely limited in what we can see in the universe and in the world around us. So light is just an electromagnetic wave. And like waves on the ocean, it can have different wavelengths. And those different wavelengths to us, in our vision, correspond to different colors. And you can see at the top of this chart that the visible light, and this is actually a very human-centric chart because it's visible to humans. There are animals whose vision is at other wavelengths. But to humans, these are the colors that are visible, the rainbow that we're used to, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. But there are much broader range of wavelengths of light than what we can see with our eyes. And if we look at longer wavelengths of light, which correspond to lower energy light, that's what's called infrared light. And if you're standing next to somebody or you're out in the sun and you're feeling warm, that's mostly infrared light that your skin is actually sensing. If you didn't know it, your skin is actually an infrared eyeball. You can sense where infrared light is on your skin and tell what direction it's coming from. And what we're doing with this telescope is using a camera that's specially designed to look at these part of the infrared spectrum, because the features that we're interested in from these galaxies that help us distinguish if they're at the same distance as those piles of gas are at those infrared wavelengths. So that's a little introduction to the colors of light that we're looking at. So in terms of what we can do with infrared light, let me pull up this chart. So in this chart, we have an example of a more zoomed in example of this electromagnetic spectrum that zoomed in to sort of ultraviolet to infrared light. And you can see here the red, orange, the blue RGB, the red, green, blue that we can see with our eyes, and then the wavelengths of light stretching into the infrared, which can be run from about 1 micron, 1 millionth of a meter, to about 100 microns. And what this chart shows is what happens to infrared light as it comes through our atmosphere. So if you were to send light of all colors through Earth's atmosphere, our atmosphere absorbs a lot of those colors, and that's what these black dips show. So at visible light, almost all colors of light make it through the atmosphere, and that's why we as humans see those colors, and our eyes are sensitive to that. But at infrared wavelengths, the water and other things in our atmosphere absorb a lot of the colors of light, and we can't see them, except for some specific wavelength ranges. So some of these wavelength ranges that are these gray bumps, those are the colors that we're observing in. And we're actually in this bump here, which we call the K band. So we're looking at light that's in this region of the spectrum that is allowed through by our atmosphere. If you go up in an airplane, or even better to space, then the atmosphere is not in the way and you can see all these different colors. And that's one of the advantages of going to space. But so we're observing here at one of these colors. And astronomers, when they look at the sky, what we do is we don't take color pictures. We take black and white pictures or grayscale pictures, but through different filters. So we might use a red filter, a green filter, and a blue filter, and then we can combine that together to make a color image. Today, we're looking at one filter called K-band. That's an infrared filter that's at a wavelength of just beyond 2 microns. These are infrared filters, and these are even further infrared filters shown in this plot. So we're using a filter that lets through light at these wavelengths. And again, this shows the colors that are missing because of our atmosphere. So the filters are designed to match what light comes through our atmosphere. I don't think that's all that useful. One of the problems with the infrared observations, though, is that the Earth is warm and our atmosphere is warm. So in addition to the light from these extremely faint, extremely distant objects, we're also collecting the light that our own Earth is giving off, that the warm telescope is giving off, that our warm air is giving off. And as a demonstration of that, this plot shows how much light you get from the background, things that you don't care about, our own air, our own atmosphere, things that glow around us, as a function of wavelength. And at visible light, it's down here. It's a tiny amount of light. And you can see as we get to on Mauna Kea, as we get to longer and longer wavelengths, and we're observing here, the sky background gets higher and higher. And this is not a linear plot. Each tick here on the vertical axis is a factor of 10. So there's almost 100 times more light. You got something, Jamika, you want to ask?
Oh no, I was just trying to measure that. You said a factor of 10, and I was looking at
Yeah,
your
this is a
high
factor of
power.
10. So compared to visible light, we're up here somewhere. So yeah, it's about 100 times brighter in the background than at visible wavelengths. So this makes finding those faint objects challenging. It's kind of like staring into the sun at visible light, right? You know, if you go outside and you try to take a picture of something with someone sitting in front of a bright window, they're washed out, right? So we are contending with this very, very bright background. And so in our observations, in our observing planning, and in the kinds of data we take, we actually have to plan for that. And one of the ways we do that, one problem is that if you get all that light coming on your camera, it gets saturated. Everything just becomes blown out white. So you have to take very short exposures and add them up. That background, because it's due to the warmth of the earth and things around it, also changes over time. So you also have to measure that accurately. So we do all kinds of techniques like taking a picture and then moving the telescope a tiny bit and taking another picture and then subtracting them from each other. And that removes the background at that moment. But an hour later or even 10 minutes later, the background level could be different. And if you just try to, subtract one image from another long time apart, it wouldn't work. So we do lots of different techniques in infrared astronomy to get rid of the pesky background light. So when we look at the observations that are being taken, it's going to be like picture, 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 picture. I'm not sure what the exposure times are that we have today, but they're pretty short. Whereas I often observe at visible light, and we might take pictures that are 5, 10, even 30 minutes long, and we just press go, and then we drink coffee and chat about science or not science. So these observations require a lot of planning and a lot of separate exposures and a lot of processing later. So let me see if I can, so in this case, I'll stop the share. What we're doing is we're looking for galaxies that are at a specific distance from us. And I'll try to bring up some slides that are related to this. So the idea is that one way that you can find them is that you take a spectrum. You make a rainbow of light from the galaxy and you look for the fingerprint of specific atoms whose wavelength you know what it should be. And because of the galaxy's motion away from us, that light is shifted to the redder colors or further into the infrared. And then from that amount of that shift, you can infer the distance. If you have enough light from a galaxy to split it up like that, that's great. But these galaxies are really far away, so it's really, really hard to do that. We just don't have enough light to do that. So instead, what we're doing is we're taking pictures of a part of the sky in this infrared filter that covers a wider wavelength range. And then we're going to we've taken pictures or will take pictures in a very narrow filter, a filter that lets through only a very specific color of light, which corresponds to the color at which these galaxies would have a very, very bright extra amount of emission due to a specific atom. And so the
So Roy,
galaxy,
I just wanted to jump in for a second. So I'll cover this later when we talk
okay,
about the the observations themselves and our future observations with
okay.
Subaru. So I'll show some diagrams to illuminate that because it's kind of hard to visualize. But I just wanted to show people that like just some common examples, at least here in Hawaii, of spectroscopy. Um, so these are all pictures. Actually, these two pictures I took, and one is taken by the National Astronomical Observatory of Japan. These are all rainbows. So we get rainbows here quite a bit in Hilo. I'm in Hilo, so Roy's on Oahu, different island. So Hilo is a rainforest, and this is just outside of our Gemini North Base facility. That's where I work. We have a rainbow almost every day coming out. This is in our Volcano National Park, a rainbow there, and then a moonbow, which is on the summit of Mauna Kea on the very large mountain, one of two very large mountains on this island, where a lot of the observatories and the largest observatories in the northern hemisphere are. So this was caused by the moon. And so it's just in this case, it's a refraction of light. So you have white light coming in from a source, and it hits a refractive element or a dispersive element and breaks the white light into its constituent colors. And so when it rains, you have the light hitting a raindrop, and each color of light has a different energy. Red light having less energy than blue light bends less. And then you get the dispersion and you see the rainbow. And so this is a very, very useful tool. Astronomers basically do one of two things, very broad brush picture. We make a rainbow or we take pictures. And so tonight we're going to take pictures, and there's advantages to both, advantages and disadvantages to both, that we'll talk a little bit more about later. So I just want to jump in and share that, right? I think you're muted right now, right?
Yeah, and so here's an example of some of the kinds of rainbows that we look at. So the rainbows that we are used to talking about as rainbows, like the ones Brian showed that we have tons of in Hawaii, come from continuous light. So in that case, the sunlight or the reflected sunlight off the moon, which is a hot light source, goes through a raindrop, and that raindrop spreads out the mixed up colors by wavelength. Different colors of light get bent by different amounts as it goes through the raindrop or as it bounces around the raindrop, and it gets spread out into a rainbow. That's Isaac Newton's first experiments with realizing that light is made of a mix of colors. But not everything makes the kinds of rainbows that we're used to seeing. If you have a cloud of gas, the physics of it are different than of having like a hot light bulb. And that cloud of gas still gives off a rainbow. We can't perceive that rainbow with our eyes usually. We need to have a tool that does it, like a prism or a grating. And then we can see that it only gives off very specific colors of light that correspond to specific wavelengths. It's like as if in the ocean, there were only waves that were 1 feet apart, 3 feet apart, and 10 feet apart. That would be weird, but that would be correspond to this kind of light. And these specific colors depend on exactly what your kind of gases or molecules you're looking at. And if this gas is moving towards or away from you, these shift bluer, or usually it's moving away, to different colors. But the fingerprint, the pattern remains the same, it just gets shifted. So in our case, we're looking for galaxies, as Brian will say, we're looking in one filter that's focused on one of these bright colors, and another filter that's focused on a broader range of colors, but including that. And galaxies that are giving off this specific color of light will appear brighter in the filter focused on that versus the broad filter compared to galaxies that don't have this feature. And in reality, most things are a mix of things. You can have a light source behind the cloud of gas, and then you get absorption. You can have the cloud of gas also glowing. So you get in astronomy, we have very mixed up spectra. And a lot of what we do is just like detectives looking at the mishmash of fingerprints on a doorknob, trying to disentangle what is really there. So right now, we're not spreading the light out into a rainbow. We're taking pictures on this telescope sort of in the infrared, but through that K-band filter that covers a pretty wide range of infrared light. And then we have another telescope that happens to have a specific filter focused on one of these colors that our galaxies will give off if they are at the distance where this gas is. So that's our goal, is to find those galaxies to see if they're there using pictures instead of rainbows, instead of spectra. So today we're just taking pretty pictures. Actually, and as we take these pictures, they won't even look that pretty because until we add up hundreds or thousands of pictures and subtract the background and take away any defects in the camera and stuff like that, they're just going to look like tiny points of light. Or if we subtract one picture from another, we might see that as we go in the night. We'll get rid of the background, but we'll have a positive and negative image, and then we'll have to, you know, do some math and do some shifting and adding to make pretty pictures in the end. So that's the broad brush I wanted to give about infrared astronomy and the types of data that we're taking as pictures in this case, the wide infrared filter. And I'll also add that we're using this telescope. Different telescopes have different cameras with different capabilities. So if you, depending on what science you want to do, you might have to use many different telescopes in the same way that at a construction site, no one vehicle takes care of everything. You need a crane, a front end loader, a dump truck. Maybe you need a bigger crane and a smaller crane, a crane that's slow but can lift big heavy things, and a crane that can move little things around quickly. So we often have to bring a whole suite of tools that operate with different kinds of cameras, that take pictures or make rainbows, that are big telescopes or little telescopes, that look at radio light or X-ray light, and put to create a whole picture the same way we need all those tools to make a whole building.
So, Roy, I'm glad you brought that up because we've had many sessions with you and the rest of your colleagues, and you're using different telescopes. As you said, this is the very first time you've been using this Magellan telescope. What is different about this telescope and the particular instrument that you're using that's different from the other instruments and telescopes that you've used for these observations?
In this case, we're using Magellan because our collaborators have access to that telescope, which is one of the, not all telescopes are accessible by everyone. There are publicly funded telescopes that any astronomer, say in the United States, can use. There are ones such as Keck Observatory on Mauna Kea, which is primarily Caltech and University of California with smaller components to the rest of the astronomy community. And because these telescope time is very precious and hard to come by, we have to sort of cobble together all of the tools. And for instance, these observations, we could take these K-band images with some other telescopes that we have access to, but we wouldn't be able to get enough time on the telescopes that I can or Brian have access to actually do all of the science. So we're taking, let's say I have access to the Subaru telescope on Mauna Kea, and that happens to have that narrow band filter, which no other telescope has. So we're going to take the precious time we can get on Subaru to do that piece of the observing, and then use another telescope length, in this case Magellan, which our collaborators at Carnegie Observatory have access to, but I don't have access to at University of Hawaii. And so, and then we have collaborators at University of California who have separate access to the Caltech observatories or also to Keck. So, and Brian's at Gemini Observatory. So we're trying to piece it together from all of our contractors
Which
as
is free and open to all, I'll just mention. Free and open to all.
Gemini. Yep. Your taxpayer dollars at work.
Gemini. Yeah.
Very important. So sometimes there may be overlap between the tools, but your access to the time is very limited. And that's because the astronomers are all competing for the time. The way astronomical observations work is not just like, oh, I'm going to go to the telescope and take data. Every 6 months, we have to submit proposals to a committee, to whichever committees we have access to, called time allocation committees. And they look at all of the proposals from the astronomers who want to use a given telescope, and they rank them. And usually people want more time than is available, 2, 3, 5, 10 times as much time as is available. And so your proposal is competing with others, and you might not get the observing time. I mean, telescopes like Hubble and James Webb, people are asking for 6 to 10, sometimes 12 times as much observing time as is available. And there's only one Hubble and one James Webb. There are multiple telescopes, for instance, that could observe these observations we're taking tonight, but the pressure on all of them is high. So we are making decisions about which of us has best chance to get the time that we need, the kinds of observations that we need, and to put all the pieces together.
Okay, I see, I see. And then so because you're getting data from different telescopes, what is it like to kind of combine that data in order to help reach your research goals? Because I'd imagine there's a lot of combination that has to happen in making sure that things are aligned correctly when you're looking at the different data sets. So I'd imagine that's also a lot of work, and sometimes possibly does some of that data have to be thrown out because it doesn't quite line up with some of your other observations?
It really is. I'll go back to my construction site analogy, right? The plumbers need to talk to the electricians, need to talk to the drywallers, and when they don't, you end up with an outlet in your toilet or something, right? So, but we have just like those trades, most of us have some kind of specialization where we're more familiar with one kind of data or a few kinds of data or telescopes than other people, and that's why we work in these teams. So actually the team, Nima, who's observing, their team has started out with a survey called LATIS, which we'll hear more about, but they were doing this looking for the gas, the absorption from light passing through this distant gas, which I've never done. I've never done that kind of mapping. I've never done that kind of data taking. And so they did that and found these clouds of gas. And we, by chance, our group that Brian will talk about more, C3VO, has been looking for the galaxies that live in groups or clusters in the early universe. And it just so happens that we had overlapping parts of the sky that we were looking at. And we said, hey, let's work together and figure this out. Because we're both interested, both teams are interested in the same kind of science, and yet neither of us could do the whole thing by ourselves. But it is a challenge. I mean, we have a coordinate system on the sky. So when we process our data, we have to make sure that the images, we figure out where we are looking on the sky, and this object is at this coordinate. But it can be confusing. When we look with different cameras, we have sometimes more finer or worse resolution. So you can imagine looking down on a stadium full of people and your eyes are blurry. Then you can still kind of see that there's blobs of people. But then you look at it with clear vision and you can see the individual faces. But then you have to ask, is that blob I saw over there, does that correspond to this one person or these two people? Or maybe these two people are sitting back to back and now they're combined into one blob and I can't tell them apart. We're always struggling with that kind of stuff. And we often have to account for that and say, okay, I can't actually quite tell what this is, or this might be a combination of two objects or something like that. So there are those complexities and you can make mistakes. There have been times when we've taken pictures of an object and then we go take a spectrum of it. We make the rainbow, and the rainbow tells us there's actually two objects at different distances sitting right on top of each other. And we can tell because we can see the different fingerprints shifted by different amounts. But when you just took a picture, it was just one blob. Or we took a picture from the ground and it was one blob, but then when we took a picture with Hubble, it looked like that. Right? So we can, those kind of things happen all the time. And then you have to think about, this object might be really interesting. Is this five separate objects, or is it all pieces of one object, my hand, or are the fingers separate things? And the physics might be different in conclusions like that. So there's a lot of interpretation and thinking, and often doing things over and over again and going back and rechecking and learning something new that goes into it.
Thank you, Roy. Thank you. I appreciate that. And then you talked about this Y collaboration. So this is a couple of teams working together. Um, is that common when doing this kind of research that you would collaborate with another research team?
This has become the old days. In 100 years ago, Edwin Hubble went to the telescope and took his own photographic plates and made his measurements. And, he might have had some helpers, but it was a lone astronomer kind of thing. But that was back in the days when all we had was visible light and pictures for the most part, early days spectroscopy. There were teams then even of like the computers that are famous at Harvard, the team of women who were analyzing the plates. But as we've grown in sense of having many more tools that operate at X-ray wavelengths, radio wavelengths, ultraviolet, infrared, all kinds of different tools, it's become impossible to do it all on your own. So having multiple teams working together has become much more the norm. And that has extended to very broadly. I mean, things like gravitational waves. The LIGO team itself is thousands or hundreds of people that is looking for gravitational waves. And when they get a detection of a gravitational wave, they don't know exactly where it's coming from. They kind of say it's in that part of the sky. And then telescopes all over the world with all kinds of other teams start looking for it, like we have the Pan-STARRS telescope. And then when they find and pinpoint, oh, it was this explosion, then another team might have to come and take a spectrum, the rainbow of that object. And nobody could have done it on their own. So these kinds of like collaborations in and of themselves have become very common, and collaborations of teams have become very common, where people are bringing their own big teams together, but all with their own special data sets or expertise. And then you got to fight over who, no, and then you break up, like, this is the science question I'm interested in. Can I kind of use your data for it? And you've provided your expertise in processing that data, making those measurements. So you'll become part of our list of authors on the paper. You can think about the science, but maybe this isn't the science that you're that interested in, but you've done a lot of work getting that information and processing it so that I can use it. And vice versa. I might hand them our data and say, okay, run with it and do your science, but credit those of us in our team who've helped make it happen.
And are all the members of your team PhD astronomers, or do you have
We had yeah, I didn't stage. Joel, did you stage that question? Joel is just graduated undergrad, and he started working with us in his senior year. I run a program called Research Experience for Undergrads here at IFA. So we have undergraduate students coming to us for the summer, working with our graduate students, with our postdoctoral researchers, with our faculty, with our staff. So we have many different levels of people. I think on this call, probably Brian and I are sadly, I'm probably the old fogey here, Brian, is that right? So I'm probably the
I can
most,
confirm, right? I can confirm.
by
I've done the
age
math.
at least, I'm the oldest person here. So from our team, but our team has members who are senior to me, and we have members all the way down to I don't know, even down sounds bad, right? All the way across to undergrads. So we have people all working on different aspects of it. And so in a way, there's an education component to becoming an astronomer, and there's also sort of an apprenticeship component and just doing the work, doing the research, learning, starting from the simpler stuff, the more technical bits and pieces of data processing to what is the physics and the science that's going on. So we're very vertically integrated in that sense.
That's wonderful. So what's the current status of the science observations? Where are we with that? Because I know when I joined, you're already on Sky, yes?
I think I don't have the observing window in front of me. So for instance, usually when we're observing, one or two people are in charge. And so some of us who are here on the shadow session are only on the shadow session to provide the scientific background or like answer questions. And Nima, who's observing, and I think Brian has access to the observing windows, they're busy actually talking to the telescope operator and taking the data, so they may be challenged at times to talk to the people on the shadow call. But I think Brian knows.
I'll jump in right here. So Nima is actually going to join us now. So I'm running two different Zooms right now, and so I have one connected to the operations that's connected to Chile, and then Nima's on that call, and he's just now going to jump over. So he's driving the telescope. He's not driving the telescope. He has the roadmap for the universe tonight, and we have a telescope operator in Chile who's driving the telescope. And so Nima is going to join us shortly to talk about some of the science and some of the observations to get us oriented. So um, while he's getting on, let me. Okay, so oh, Nima just joined. Okay, so I just wanted to orient people. Let me this. So I just wanted to orient people as to where we are. So I'm in Hilo, Hawaii, on the Big Island. Joel is in Georgia. Roy is in Oahu, and Nima is at IPAC, so in Pasadena. And we are observing in Chile. So as Roy said earlier, this is truly a worldwide endeavor. This is where the Magellan telescopes are. Roy said there's only one Hubble, one James Webb. Well, there are two Magellans there and two Geminis. And so the two of them sit here. We're using the Baade telescope tonight. And so this is a map of right now. This is a service that the observatory provides. So this is information on the conditions in the location. So I have two different monitors up for the weather. This one is the Gemini South monitor, and it's showing cloud cover around the location of Gemini South. Gemini South is just 4 hours drive in between the Magellan telescopes. The Magellan telescopes are up here. Serapecan, where Gemini South telescope is here. And so I can use the Gemini South monitor to also monitor the Magellan status. And then this is from uh, Carnegie, essentially. And this is showing the cloud cover in the location of the Magellan telescopes, which is here on this little inset. And so you can see it's a cloudless night, although the clouds are creeping a little bit, but low lying. You can see the moon is out. This is a fisheye view of the sky at the moment. And so the moon is out, and I believe the point in the sky that we're pointing to is this little blue circle here, if everybody can see that. And so we're basically pointed directly up towards what we call zenith in the sky. And this speaks to one of the questions that you asked earlier, Jamika, which is that there is another few reasons why we might want to use the Magellan telescopes for these observations. So Subaru, the Subaru telescope on the Big Island of Hawaii, is at a latitude of plus 20. The Magellan observatories are located at a latitude of roughly minus 20. And we're looking in the southern part of the sky tonight. So we're actually looking down south. And so it helps a lot. Your location on the Earth matters about what part of the sky you can see. So it helps a lot to have a southern hemisphere observatory looking at the part of the sky that we're looking at tonight. And so there's plenty of very interesting things in the north, and the northern telescopes can reach this target. So this is why we're able to do Magellan observations and Subaru observations. So this is a multi-hemispheric target, but it's more ideal to observe from the southern hemisphere on Earth because it's in the southern part of the sky as we orient. And so Roy was talking about the precious time on Subaru. We have even less time on Subaru than we would have on Magellan because we would never see this part of the sky straight up ahead in Hawaii. We would see it down on the horizon. So that means it's up in the sky for a shorter period of time. And so we have less time to be able to observe it. Tonight, we have the luxury of observing from minus 20 latitude. And so this thing is up in the sky, right directly straight up. And this matters because it not only the amount of time that you can see this object or this part of the sky, but it also matters how much atmosphere you're looking through. So if you're looking straight up, the amount of atmosphere Roy showed earlier, the atmosphere is bright in near infrared photons and near infrared wavelengths. And so if you look through the sky straight up, you're looking through the minimal amount of atmosphere. If you're looking right on the horizon, or you're looking at halfway in between, you're looking through a lot more atmosphere. So it's brighter, there's more turbulence, it's generally worse observations. And so it's really, really helpful to have multiple tools to be able to observe here. So I'm going to pass over to Nima. Nima is an expert on the science, the foundational science that started these observations. And in fact, much of the observations for the LATIS survey took place at the Magellan telescope. So let me stop sharing. I'll pass over to you, Nima.
Welcome, Nima.
Hi everyone. Thanks for the nice just information and introduction, Brian and Roy. That was great. So I'm Nima Chartab. I'm a scientist at Caltech's IPAC. At the moment, it's midnight here, and I'm in my home office remotely observing with Magellan telescope at Chile. The observation that we have right now is a part of an exciting program, the LATIS program. And I joined this program 3 years ago when I started my postdoc at Carnegie Observatories. And today I'm going to give you a brief introduction about the project and what we are observing tonight. Let me share my screen. Can you see my screen?
Yes, we can, Nima.
Great. So LATIS stands for the Lyman Alpha Tomography IMACS Survey. This is a survey that's started with scientists at Carnegie Observatories. I should name some of them the PIs of the program, Dr. Drew Newman, Gwen Rudy, and Guillermo Blanc, and also Dan Kelson, who are the main PIs of this program. And in collaboration with other scientists, they formulated this survey. And I joined this program in the last stage, kind of in the last semester that we were taking the data in 2022, but the program started in 2018. So it was a kind of 5-year program. So here in this image here, I am showing the Carnegie Observatories in Santa Barbara Street in Pasadena. So it's the home for dozens of scientists, engineers who work together to discover the universe. So they do kind of fundamental research there, and engineers and scientists work together to build instruments that we can use to study the universe. So Carnegie Observatory also manages the Las Campanas Observatory, and this observatory is located in Atacama Desert, one of the greatest kind of locations. It is exceptional because it's very dark spot on the Earth and very dry. So it's very ideal for observations. And right now, for example, we have seeing of 0.49, which is great. Last week we had 0.4 arc seconds seeing, which is great. So we are getting very sharp images and sharp spectra in this location. And one of the great telescopes there is the Magellan telescope. It's two identical telescope, 6.5 meters. And you can see the image here, the Baade and Clay. And tonight we are observing with Baade. And there are many instruments mounted on these two telescopes, but the one that we used a lot for this program is IMAX. And right now we are using FourStar. The IMAX is the optical imager and also multi-object spectrograph. So we get the optical images and also a spectra of each galaxies. We did thousands of spectroscopy with IMAX. And also, FourStar that we are using tonight is near-infrared imager. So it has different broadband, medium band, and narrow band filters that we can use to image the sky in near-infrared. So before jumping into the LATIS details, I want to start with the concept of Lyman alpha tomography. What's Lyman alpha tomography? Here I'm showing an animation that you can see if there is a background source like a bright quasar, if the light from that quasar travels through the intergalactic medium, it hits the neutral hydrogen in his path in the medium. So in that sense, in the spectra of that quasar, we can see some absorption features, which are the Lyman alpha absorptions. So the strength of these Lyman alpha absorption is correlated with the amount of neutral hydrogen that we have in this line of sight. And that is also correlated with the amount of dark matter. So by using all these line of sights, we can map the dark matter in the universe or large-scale structures. So here I'm showing some data from simulation that you can see, for example, with hundreds of sight lines, we can get kind of this from this map, we can go to this map. This is kind of, we sampled this map by all these 800 sight lines. And you can see that in a big picture sense, we are kind of reconstructing all the density structures that we can see here, all the large scale structures. The red regions that we have the strong absorption corresponds to the larger structures, protoclusters, because we get more amount of matter there, so we get more absorption. And the blue regions shows the voids, where there is no negligible amount of neutral hydrogen there since the dark matter. The good thing about this, when we study large-scale structures, we usually astronomers use the galaxy, the number density of galaxies. But the problem with number density of galaxies, you cannot get the complete sample of galaxies. There are two ways you can get complete sample of galaxies, but in that case, you don't know where they are exactly. You have some uncertainties in their position, in their redshift. So you need to mitigate that thing with some methods that we do to just reconstruct the large-scale structures. But this method, the Lyman alpha tomography, can provide those maps independent of galaxy population. So this is great. So it doesn't matter what type of galaxies do you have in that structure. You have the neutral gas, so you will get the absorption, so you identify that structure. So the idea of this Lyman alpha tomography is pretty old, but the idea of, but astronomers usually use it for the spectra of quasars, but using it with bright galaxies known as LBGs, Lyman break galaxies, to reconstruct the density maps is relatively new. In the last decade, people trying to use different data to map these structures. So motivated by this technique, a team of scientists at Carnegie Observatories formulated this Lyman alpha tomography IMACS survey, which is for mapping the universe at the redshift 2.2 to 2.8, which is the critical epoch in the universe, because at that time the universe was very active, building lots of stars, lots of feedback processes. So that's very important epoch in the universe. And it was a 5-year program from 2018 to 2022. And we got around 60 nights of observation and thousands of spectra with IMAX instrument and Baade telescope. And we got very deep exposures for galaxies, for that background galaxies that we use to reconstruct these structures. And the depth is around 12 hours per source. It's pretty deep to get 12 hours spectra for each sources. And also, this is the size of this, the survey area is pretty large. It's 10 times larger than the previous surveys like Clamato, which is done with Keck telescope. And this program is done in 3 different fields. That's the bottom one is the Cosmos field. This is a well-studied field, lots of space-based, ground-based data, lots of spectroscopy. So this is great. So astronomers, we have lots of ancillary data that we can combine with lattice structures to study structures. But on the top, there is D1 and D4 fields. And the D1 field these are the CFHTLS fields. But if you look at the one in the right top, you can see that this the black boxes are the pointings of the IMAX. So these are the regions that we covered with LATIS survey. And the green green region, the green enclosed region, shows the region that we have near IR data, near infrared data. That you can see here that we are missing near infrared data in some part of our survey. That's what we are covering tonight. We are covering those regions that we don't have near IR data to get kind of homogeneous map of near infrared, as Roy and Brian mentioned, to select galaxies, the galaxies which have the emission line. But for that, we need to combine it with narrowband data to select those galaxies.
So Nima, I'll just jump in here for a second. If you go back to the last slide. So yeah, so each one of the maps that Nima is showing on the right-hand side, those are archival images in the background from another telescope. And he's overlaying both the IMACS observations that the LATIS team took, which are the black shapes there, and then other imaging or spectroscopy data that other teams have taken. And so, as Nima said, there's a lot of virtue in these fields. He mentioned the CLS. So this is the Canada, France, Hawaii Telescope Legacy Survey. There were 4 fields of this survey. This is a Hubble-sized telescope on the summit of, or near the summit of Mauna Kea. And they imaged in 5 bands very, very deeply in these 3 fields. And so this was 2 decades ago. And this set the basis for a lot of the surveys to come for all of these wonderful observations from the ground and from space to be taken. And so one of the surveys that came after the Canada, France, Hawaii Telescope survey was this survey called WORDS, which is this green one in the top 2 panels. And this was a near-infrared imaging campaign from the south, from Chile. And so that survey was looking at a specific type of science, and it turns out that we need to supplement their initial pointing. So this is one of the poorer of these fields. It wasn't as highly studied as, for example, the bottom field there. And so it requires more observations in order for us to fully utilize it. But just to give people a sense of scale, a full moon on the sky is roughly about, let's say, 2/3 of the size of the bottom image there. So when Nima says that the survey area is quite large, this is basically the size of 3 full moons. And so it's still a very small portion of the sky. But for astronomers, especially when you're looking this deep with these huge telescopes, that's a large survey. So that's, I mean, if it requires 12 hours of observation just staring at these patches of the sky, it's not like we can just go out and get hundreds of hours of telescope time on a whim. It requires, as Roy mentioned, a lot of, we need to argue to other scientists to say, this is a really great idea. And telescope time on these large telescopes is very precious. And so to get hundreds of hours, like Nima and his collaborators did on Magellan, it must be a really good idea.
Hey, thanks, Brian. So here I'm showing the final product of this survey, which is done with IMAX in one of the fields, in Cosmos field, the one that in the bottom. So here you can see this animation here shows the evolution of these large-scale structures as we move in the redshift. We are starting from redshift 2.2, and we are going to 2.8, and you can see different structures. As I said, the red regions, which are the protoclusters and the structures, and you can see the voids in the blue regions. And this is kind of the beginning of the follow-up observations. We identify these structures, we go and look at them with other telescopes, we look at the properties of galaxies inside them, and so on. Some of these structures are very well known. For example, at redshift 2.5, there are very well-known structures. For example, the Hyperion clusters that you can see, protoclusters that you can see. But there are also some protoclusters that we found only based on the lattice maps, where you don't have that much overdensity of the galaxies, but you can see these strong absorptions, the Lyman alpha absorptions. So these are the interesting targets for follow-up observations. So if I want to summarize the goals of the LATIS survey, the first one is twofold. The first one is to map the structures in that redshift and look at the different properties of galaxies as a function of their environment. That properties could be the rate of the forming stars or their metal content. But the other thing is, regardless of their environment, we got thousands of great spectra, kind of this homogeneous survey in these three fields. So we can use that to study a spectra of galaxies regardless of their environment. For example, we can look at their stellar metallicity, their iron abundances, the metallicity in the stars of these galaxies. Here you can see the individual spectra that we got for different galaxies, and you can see there are lots of absorption lines. Most of them are from the interstellar medium, but there are also, if we stack all of them together, we will end up getting very tiny absorption, which comes from the stars inside those galaxies, which is the first project that I did when I was in Carnegie. So we took the thousands of spectra and we stack all of them to kind of get one high signal to noise spectrum of all the galaxies that we have in the lattice. And this is the very high signal to noise spectra you can see here. There are this big absorption lines mostly comes from the interstellar medium. We are not interested in those in this study, but we are interested in very tiny absorptions here, which mostly comes from the iron element in these galaxies. So we can use the kind of the depths of these lines, the strengths of these absorptions to measure the abundance of heavy elements in these galaxies. So we did that, and this small panel you can see here shows this the kind of metal content of galaxies, the fraction of iron to hydrogen in these galaxies as a function of their stellar mass. We knew that the galaxies with higher stellar mass should have higher amount of metallicity because they have more time to produce those elements, and also other feedback processes that can make this kind of shape. For example, the feedback processes are very strong, for example, for low mass galaxies. It can expel all the material to the circumgalactic medium or intergalactic medium. But the good thing that we found is if we go to the very massive end, it seems that it flattens. It's not going, it's not increasing in the very massive end. If we translate that to the amount of outflow we have from the galaxies, here we are translating it to the outflow rate in galaxies, outflow of this gas, this metal-rich gas. And if we look at that rate as a function of stellar mass, we can kind of use some analytic models to get this kind of trend, which is from observation, which is from our metallicity mass relation. And we compared that with some simulated data like TNG 50 data, and they also found the similar turnover in this trend. And the turnover here in the simulation is because of the black hole activity in these galaxies, the black hole activity in the massive galaxies. So our result here just provides the evidence for black hole activity in massive galaxies in that redshift. As I said, in that redshift of 2.5, redshift 2, the galaxies are very active. The feedback processes are very strong, and that could be one of the evidence for that. This is the result that's published, and this was one of the results that we use all of the data regardless of the environment. And we are in the process of using, looking at—
Nima, can I just jump in for a second? If you go back to the last slide. So there was a question from Vani about what role simulations play in understanding or interpreting the observational results or your research results in general. This is a perfect example, I think, of that, because the simulations allowed you to interpret the observational trend that you see. Is there other instances in LATIS, either in your work or in other aspects of LATIS, where simulations can be important?
Oh yeah, I think, for example, the other thing that I mentioned before is, for example, the overdensities that we are getting from these absorptions, the Lyman alpha absorption, is correlated with the amount of dark matter. Or this is also we also get this from simulation. There is no way to see the dark matter in the universe and just get this statement. We are using the different simulations to kind of validate our observations, the first thing, or inform the simulation from the observation and check the consistency to trying to get the sense about the physical properties going on in galaxies.
And
So
one of their points, so you mentioned the term redshift, and I think Roy kind of alluded to it earlier, but this is measuring effectively the distance to galaxies, and then because we're looking back in the very distant universe, we're also looking back in time because of the finite speed of light. And so this is observing galaxies when the universe was roughly 15% of its current age or something like that. So about 3 billion years, 2 to 3 billion years after the Big Bang.
yeah,
So this is really when galaxies are starting to they've formed and they're starting to build up their mass, and they're converting the gas, nascent gas that they had from their formation into a real stellar content.
that's right. So yeah, here is just one slide about what we are working on right now. These are all preliminary studies. The other thing that we are looking at is environmental dependence of other parameters like metallicity. And for that, we took all the protoclusters that we have in those three fields, and we stacked all those protoclusters and looked at the average kind of metallicity of galaxies as a function of the radial distance from the center of the protocluster. And you can see here, if those galaxies locate in the center of that protocluster, there are metal poor compared to those that are in outskirt of the galaxy. So these are the things that we can see, and this is kind of could be related to their star formation. It could be related to the gas funneling to those structures at high redshift, the cold gas. But there is debate in the literature about that. For example, this is the similar study that I'm showing here at the redshift 2, that people looked at gas phase metallicity. This is different. This is the gas of the interstellar medium. That one that I'm showing in the top is the metallicity of the stars, but this is the interstellar medium. And you can see the range of different results. Some people get that, oh, in the protoclusters, the metallicity is higher. Some people say the metallicity is lower. So there is no consistency there. Because of that, we are doing some follow-up studies with also the Keck Mossfire instrument. The Mossfire is the near IR spectrograph, so multi-object spectrograph. So what we are doing, we are selecting some of these structures that I'm showing here from the lattice map, and we are doing a spectroscopy in them to get their kind of optical spectra, rest frame optical spectra with near infrared, to get the emission lines that we need to measure their gas phase metallicity. We started this and we get some of the data for this structure here in the bottom. And for this one was the great example that when we get the spectra of all these galaxies, we discovered that there is another structure exactly behind this structure that we can see in our maps. So we got two protocluster in the same shot. So we got around 50 objects in these three masks, and we are analyzing the data, and we hopefully publish the data very soon. So yeah, that's all. Yeah, that's all I can say. Thank you.
I just want to add for the audience that you might see the word metals here and metallicity, which you think of as aluminum or gold or iron or something. But astronomers are weird, and metals are basically anything above hydrogen, more or less. So oxygen is a metal, carbon is a metal. So when we look at the metallicity in objects, what we're really talking about is heavier elements that were produced either by multiple generations of stars or black hole activity or some other high energy process that can fuse or in other ways produce these heavier elements, and is a sort of a tracer of how many generations of stars might have lived or what other kind of activity might have created these heavy elements. And so that is, as a galaxy ages, it goes from being its stars being mostly just hydrogen and with a little bit of helium and a bit of other stuff. And as those stars create heavier elements and explode and pollute the gas that makes new generations of stars, the metallicity, the amount, or as we call the abundance of these heavier elements, increases with time. So that's one of the things that we do to sort of measure how much of a history of star formation a given galaxy has had, or how many generations of stars or other things might have happened.
Oh, yeah. Thanks.
Well, thank you very much, Nima. We really appreciate that you taking the time to jump over here from your observations to show us all this wonderful science. So thank you very much for that.
Thank you. That was great. Yeah. I will log off and join to the operation Zoom, okay?
Okay, sounds good. Thanks.
Thank you, Nima.
Thank you.
So I just have a quick question. As Nima was talking about with the Lyman alpha tomography, you're able to essentially trace dark matter in these large structures. Are you finding that there is the expected amount of dark matter in these structures, or does it vary from the expected norm?
Yeah, so you're not directly, it's very hard to directly measure dark matter. In fact, effectively impossible. And so you always have to do an indirect measurement. So that indirect measurement could be from the velocity distribution of stars in a galaxy. So thanks to Vera Rubin. So the rotational speed of a galaxy, the stars of the galaxy are gas in a galaxy. That can tell you something about the dark matter content. In these very large structures of galaxies, if the system is what's called virialized, so it's kind of dynamically relaxed, that there's a relationship between the potential and the kinetic energy that's kind of equilibrium. The motions of the galaxies themselves, which you can measure, will probe what's called the potential well of that system. So you can basically measure the amount of mass that's necessarily there to create the gravity to have these galaxies move this fast. So the faster they're moving, the more potential is there, just like in anything in physics. And so there you can infer the dark matter content. However, this is very early on in the universe's history, and so this type of equilibrium is not usually reached by galaxies because the structures are still very much in formation. And so that's a kind of false friend. It will give you an idea of perhaps how much matter is there, but it may give you an overinflation of that amount. So it may cause you to overestimate that amount or underestimate that amount. There's also gravitational lensing, where by the mass associated with galaxy, a dark matter halo that surrounds the galaxy, a set of galaxies that are in a cluster, or the combination of those galaxies and the gas and the dark matter that's associated with that cluster will actually lens light. And so you can see background sources. And this is like the first image that was ever released by the James Webb Space Telescope. This was this wonderful image of this cluster that's relatively nearby, so just a few billion light years away. And there was these wonderful like cosmic strings that look like, which were background galaxies that were being lensed. And I have a picture of that I can show a little bit later. But that's also very hard because these structures are very, very far away. And so it's like you take a magnifying glass, you move it very, very far away from you. And also the lens doesn't become as powerful as you move it further away from you. So not only is it not effective at that distance, but the lens is also getting of lesser quality. And so you can't really make a good map of the lensing that occurs with these systems. And so what Nima and his collaborators do is they look in simulations. This is basically the only way. And they say, okay, if we see this amount of neutral gas that we infer from our observations, from our tomographic observations, that corresponds to some distribution of matter. And so you can look in the simulation, you say, I have 15 pounds of gas. What types of systems, like how much dark matter does there have to be? I look at every location in the universe that has 15 pounds of gas. And I see, okay, so in some cases there's 100 pounds of dark matter. In some cases there's 300 pounds or kilos. Let's use normal people units. So 300 kilos of dark matter. And so then they use this distribution and they kind of back out what the dark matter distribution should look like based off of the gas. So they can only see the light, right? Or the absorption of the light or the re-emission of the light. And so they're just inferring from based off of simulations. So simulations are absolutely crucial, but those simulations are grounded on these other indirect methods and mathematical underpinnings that dictate how the evolution of the universe goes forward.
And to sort of expand a little bit on what Brian is saying, right? And a lot of times in your elementary school or whatever middle school science class, you do an experiment of, I don't know, growing plants right side up and upside down, and you can repeat it and do it over and over and try to come to some conclusions. In astronomy, we only have one universe, and we have to make measurements of it that are often very hard, and we have to interpret those. And to understand what those measurements are telling about physics, we have to create models. And often that means putting a recipe basically for how we think a galaxy forms or how we think dark matter and gas and galaxies interact or whatever. Put it in a computer nowadays and run that recipe and see what it produces and see if that matches what we see, or it will make a prediction that we should go out and look for. And if it doesn't match what we observe, we have to ask ourselves, are we missing something in the recipe? Or do we have something dialed in wrong on the recipe? Or are our observations somehow missing something or incomplete? And we're always playing this game of trying to understand and think about what we could be getting wrong on one side or the other until we can get everything as best as we can to match up and then say, okay, I now have a model in my simulations that incorporates enough physics and gets things right. And a lot of times we might be like, we make a model and it works and it gets galaxies to look the way they do today. But then if you look at what those galaxies look like in the early universe, in the computer, they don't look like what we see. So the end result tastes the same, but the path to getting to that soup or whatever was different. And so it means it was cooked differently. So we got to figure out what that cooking process was. And that's part of the reason why we're looking at these faraway objects is we're trying to understand the history, not just where we are today and how things got to be this way. What are the steps that happened?
Yeah, and a lot of times it's both. So a lot of times the observations are wrong and the models are wrong, and then we have to improve both of them. And then the second we get comfortable and we say, aha, we finally figured it out, along comes another wavelength that we've never looked at before, or another telescope that's, for example, the James Webb Space Telescope, and it sees things that we've never seen before, and all of our models, or at least some parts of our models, break down, and then we have to go back to the drawing board and still have fealty to the observations that we had before, but then somehow modulate things to provide these new concordance with these new observations. So speaking of observations, this is what we're observing. An hour and 21 minutes in, I thought I'd show this is our observing interface. This is what Nima's looking at, and he's actually doing some on-the-fly reduction right now. And so just to orient people, so there's two screens here that contain, the leftmost screen contains effectively all the information that we need as observers to monitor the time of the observations, where we're pointed, how we're technically like guiding the telescope, um, how we set up the observations in terms of the number of observations and how we're moving while we're taking those observations. And so you can see a countdown timer there that's counting down to the end of our dither pattern. And Nima, are we doing one more on this field, or are we moving on to the next field?
Which will take 45 minutes.
We do one more at 45 minutes?
Yes,
Okay.
that's right.
Okay. So we are only looking at three small patches of the sky. We actually took observations last Thursday night. So this is our second Thursday taking observations, or Friday for most people. And we looked at two of those patches of sky. We had unbelievable weather, so we were able to stare very deep. We also have unbelievable weather again tonight. It's winter in Chile, so this is not a time of year where things are normally super awesome. But if they are super awesome, you get 12-hour nights. So that is wonderful. And so we've gotten very lucky. And so we had essentially completed two of these patches of sky on the first observation night last Thursday, and then we were looking at the third patch of sky this evening. And right before the session started, we decided we had looked deep enough at that part of the sky, so we're going back to the first and second portions of the sky to look even deeper. So we have the luxury of going even deeper than we were expecting to go. And so the top right portion of the left screen, this is the four different detectors, quadrants of this FourStar instrument. And so what you can see is an individual exposure in all of its glory. So there's you can see little black spots on the image in the top left quadrant. You can see a little white patch. On the top right quadrant, you can see like a little black circle. There's kind of like fuzziness or like little like speckles. These are all detector defects. These are all we're observing with imperfect instruments, imperfect optics, imperfect detectors. But luckily, we have a lot of time on the telescope, and we can take a lot of pictures in a lot of different locations. And so over here on the right screen is a combination. Is it, Nima, is this like one dither set?
But the one on the right, it's the last two exposures.
Oh, it's just the last
The
two.
last one, yeah, subtracted. Yeah.
Oh, okay. So it's
This-
okay. So basically just an A/B combination. Okay, so this is two different observations at slightly different locations on the sky. So because the sky is so bright, as Roy mentioned earlier, we move the telescope just a little bit, and we subtract the two images. And so you can build this up over time. We're doing 30-point dither pattern, so it means we're moving to 30 different spots on the sky and taking images, and then we're looping through that again. And so when we move, we the galaxies, the stars in the image, they move to a different part of the detector. And so when we subtract the two images, we have one spot which is black, and that's not a detector defect. That's basically a decrement of light. And then we have an increment of light where the source is. And so you can see this white light here. It's all black and white. But white means more brightness, black means less brightness. And so this is the location of a fairly bright, probably galaxy that's edge on. And you can see a lot of the detector defects that were in the left screen, those have kind of gone away. And that's partially because we're subtracting them out. Eventually, these will all be what's called flat fielded out. And so we take, Nima, did you take twilight flats in the beginning of the night? Yeah, okay.
The tone flats, twilight flats, yeah.
Okay.
And dark.
Yeah, so there's all sorts of calibrations that are needed to be taken to remove these defects, because what you want to get to is the intrinsic quality of the sources that you're looking at. So you have to remove the atmosphere the best you can, the imperfect optics, the effects of the imperfect optics, the effects of the imperfect detectors. And so Nima took dome flats where you have an illumination inside the dome of the telescope, and you take an image of that. And so it's kind of a uniform source. And so you can really see these detector defects. And so you can see the response of the detector to a known source of brightness. Then Nima also takes what's called twilight flats. So anybody who's been on a Gemini North session in the wee hours of the morning knows these very well. We basically just pointed a blank-ish part of the sky. No part of the sky is blank, but things, parts of the sky where there's not a whole lot of apparent bright objects. We do the same thing. We just move the telescope around, and we get a real illumination of the sky with not a lot of sources. We stack these in a median combined way. So we basically throw out the sources being the galaxies and the stars. And we're just left with what the night sky looks like to the telescope in the detectors that are used for the telescope. And then Nima also takes darks. So this is to remove current that's in the electronics that doesn't have anything to do with the astronomical sources. And this current is a function of time. And so if we take like a 2-minute observation, we'll take a 2-minute dark to remove this what's called dark current.
And so when Brian and Nima have mentioned things like data reduction, that makes it sound like we're reducing the deficit or our bank accounts or something like that. We're not actually making less data. I think we use that term as strong, but what we really mean is we're processing the data. We're trying to get rid of things that we don't want in there. And it's just for a comparison for people, let's see if this works with my background, but many of us have one of these devices, and inside here is a camera, and this camera has 16 million pixels, 16 megapixels, and you know how tiny these apertures are. That's why it's hard to take pictures at night with your phone. A lot of the detectors that we use nowadays are about the same number of megapixels, 16 megapixels, but a astronomical sensor that's 16 megapixels is actually like half the size of my whole phone. So it's much larger. The pixels are much larger. And we can buy a whole phone like this, I don't know, for $500 or $1,000 or whatever it is, and it has multiple sensors in it. A single astronomical sensor at the kinds of qualities we use on these large observatories can cost $50,000 or $200,000 just for the detector. And they're extremely sensitive. They're much more sensitive to light than the ones that are in here. We don't make as many of them because we don't sell 1 million or 100 million iPhones. Instead, we're building very specific detectors, of which we might make a few dozen or a few hundred for the observatories. But as a result, when they make the detectors for your iPhone or whatever, they can throw out the ones that have enough bad pixels. We can't afford to do that unless they're really bad. So we have to take the hit on individual pixels or columns of pixels being bad, and then we have to correct for that and move the telescope around and things like that. So even though our pictures don't look as pretty as what comes in iPhone, and the underlying technology is very similar in the detectors. In some cases, like invisible light, it's exactly the same kind of detector in the way it works. The sizes of the pixels, its sensitivity to light. If you take a picture in the dark with your iPhone, it's speckled like crazy. That's all electronic noise. We can't accept that in our data. It would drown out the very faint galaxies we're looking at. So we have to make detectors that are much less noisy, with much more complicated electronics. We have to keep our detectors extremely cold. Detectors that we work in visible light are typically in like liquid nitrogen kind of dewars, and infrared detectors, because the energy of the light is very low, any heat will cause extra detections in the detector that aren't supposed to be there. So we often cool them to just a few degrees above absolute zero with liquid helium. So it's a completely different kind of thing, even though the basic physics is the same. And so that's why I also don't have these kinds of detectors and tools everywhere, because a camera, what we call a camera on a telescope, in some cases can be the size of a suitcase. In some cases, it's as big as a room in your house. And modern ones cost from a few million to many tens of millions of dollars to build. So they're not the kinds of things that we can just make off the shelf. And similarly, telescopes cost a lot as well. So they're very precious tools.
Roy, I have a question here. I was just looking back at and listening to your explanation, and then looking back here at what Nima is showing us on the right side, this right image. And Brian mentioned that in the bottom left quadrant, that looks like an edge-on galaxy, potentially that bright one. Part of the research goals that you all have is to identify potentially missing galaxies in these structures. How can you determine which galaxies that you might find in your data are missing, and which ones are galaxies that have already been identified?
So in this case, I mentioned that we're taking data in two different filters, one that covers a broader range of colors in infrared light, and then when we'll use the Subaru telescope on Mauna Kea to look at the same structure, but with a filter that picks out a specific color of light. And if these galaxies are at the right redshift, the right distance, then it will have a bright emission line. I showed those different kinds of rainbows. So one of the gases in the galaxy will give off one of those bright colored lines that sits only in that narrow band filter. And so galaxies that are not at the right redshift, that feature will be outside the filter, and they'll be invisible in that narrow filter because it's looking at only a very small portion of the electromagnetic spectrum. And galaxies that are at the right redshift will be bright in that narrow filter compared to the broad filter, basically. So Brian's got some plots up there. He can take it from here.
Yep. So yeah, I just thought this might be helpful as a visual for it. So this was the James Webb image that I was talking about earlier, of this cluster lovingly named SMACS 0723. And the cluster galaxies, so this cluster is, a couple of billion light years away. The cluster galaxies are the ones that have like a kind of palish white color here. This is a star right here. And then you can see these lensed galaxies, so these kind of curvy things here and here, here. These are galaxies that are whose light is bent by the gravity associated with this massive structure. So this massive structure is somewhere around a billion million times the mass of the suns. When you add up all of the galaxies, all of the gas, all of the dark matter, it's roughly a million billion sun masses. So it's very, very massive, and it creates this gravitational lensing structures that magnifies background galaxies. And so some of the background galaxies, so these lensing arcs, these are roughly the distance. Most of them are roughly the distance that we're looking at now. So roughly when the universe was about 15% of its current age. But there's galaxies that are even older in this picture. They're not as spectacular on the image, but there's these little points, and these are also gravitationally lensed. They just don't look like it. partially because they're intrinsically small and partially because they're not lensed as much as some of these arcs here. But these are, as much as 13 billion light years distant. And so this is when the universe was like 5% of its current age. And so on the right here, this is spectra. So these are rainbows from James Webb Space Telescope. And what's being plotted here is the intensity as a function of wavelength. So Roy mentioned microns earlier. So this is 2 microns. It's hard to see, but 2 microns is where we're looking. And you can see these strong emission features, so strong spikes of intensity that happen at certain wavelengths. And you can see in this figure, it's ascribed to the excitation of different elements. And so the red corresponds to hydrogen, which is by far the most abundant element in the universe. And then the blue is attributed to oxygen emission. And so going over to this figure here, this is basically our observational setup. So tonight, we're looking with Magellan at this KS filter. So this is, again, in this case, its throughput is a function of wavelength. So how much a filter, so this is a piece of glass that sits on the optical path of the telescope, how much light it lets in as a certain wavelength. And so you're taking an image in a certain color, basically. And so this is the reddest color in the near infrared that we typically look at from the ground. Although there's redder colors. Gemini looks at redder colors. Infrared, the NASA infrared telescope facility looks at slightly redder colors. But for a lot of telescopes, this is as red as they go. And this is at roughly a wavelength of 2.1, 2.2 microns. And so you can see there's this broad filter that allows in, it's a huge light bucket that allows in a bunch of different wavelengths to come into the detector. And so we were able to see it on the detector. So that's what we're seeing on the detector tonight. Then there's this narrowband filter. This is, in this diagram, it's called NB2071. And this only allows very specific wavelengths of light to come in. So roughly 10% of the wavelengths of this big broad filter it allows in. And so you can imagine if one of these spikes of intensity coming from one of the elemental excitations here just so happens to fall into this filter. So you see basically nothing, 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 and then huge spike. And so if you place this huge spike, you look at galaxies that are far enough away, because when they're further away, these spikes move to the red due to the Doppler shift. And so when they're at a certain distance, you'll have spiking right in this narrowband filter. And so what you'll see is a very a strong color difference between what's in the narrowband filter and what's in the K-band filter. And so we'll take our Magellan observations from tonight, we'll contrast that with Subaru observations that are going to come up later this year, and we'll look for things to pop out. And so so this is the target for tonight. This is lovingly called LATIS 2 D400. A very clever name. What that refers to is the second generation of the LATIS survey. So their survey is now complete, and Nima showed they have this amazing survey of thousands of galaxies with incredible deep data. So they've finalized their survey. We're looking in the D4 field. This was the Canada, France, Hawaii Legacy Survey D4 field. So it's a specific location in the sky. And 00 means this is the most massive structure that was found in this field. And in fact, in the entire LATIS survey, this was the most massive structure that was found. And so this structure is also something like several billion million solar masses times the mass of the sun. And so it's a very, very massive system, analogous to this SMACS cluster that's sitting in the very early universe when the universe was about 15% of its age. And so what we're observing with this plot here is an intensity map based off of the IGM tomography maps that Nima talked about. And so this is where the LATIS survey says that there should be a lot of gas and therefore a lot of galaxies and a lot of dark matter. And so these black points are where we are going to point with Subaru when we get the Subaru observations. And so on the right here is a picture of all the lattice representation of all of the lattice massive structures. And what's being shown on the left is basically a representation of mass. So the more massive things are on the left here. And then on the y-axis here is the galaxy content of those structures. And so when you go further up in this diagram, it means there are more galaxies in that structure. And so these green shaded regions and this black line all come from simulations. And it's the expectation of if you have a lot of gas, it's basically saying if you have a lot of gas, then you should have a lot of galaxies. Not really surprising. You should that gas should coalesce, it should fragment, it should coalesce and turn into galaxies. But there's lots of systems that seem to have not so many galaxies given their mass. And there's this system which has a ton of galaxies given its mass. And so why the heck would you have some systems that the same exact mass, same exact gas content, have tens, hundreds of times more galaxies, so this system versus a system that basically has no galaxies. And so all of these systems we've targeted, we've observed with Subaru, except for this one here. And so these are the observations that we're taking tonight with Magellan, so Nima talked about this word survey and I mentioned about it. So it has this kind of weird pattern. This is the K-band data, the K-band observations that were taken already. It's not really uniform. It was done kind of ad hoc for a specific type of science. And this system here actually sits in this region right here. So there's big holes in the coverage, this black part and this black part here. We have no K-band observations there. And so these three purple locations, the background image here is the words K-band image, and we're filling this out so that we can observe the whole entire system with Subaru. And so when we combine these two, this is based off of observations that we took previously. I'll start this movie. And so what's being blinked here is the first one that doesn't have the streaks through it is a K-band image, and that K-band image comes from words, so from Chile. And the image with the streaks through it is a very rough processing of observations from Subaru. And what I'd like you to focus on is like systems like this here. So you see this red circle right here. You can see in the K-band image, you can barely see anything there. These things are billions of times fainter than the night sky, so it's really hard to see them. But you see in the narrowband image, the one with the streaks running through it, it actually pops out, so it's like a flashing light there. And this is because we've captured an emission of hydrogen directly in those wavelengths of that narrowband. And this is exactly at the distance of one of the superstructures that we know about from other observations. And so each one of these red circles represents a galaxy or a candidate galaxy that is a part of this structure. And this is just one little tiny portion of that structure. So that's the hope, is that we take these observations, we contrast them, it's just contrast imaging, we contrast them with the observations that we take from Subaru, and out pops a bunch of galaxies, and we say, hey, there's all the galaxies from that system, and we can actually measure, because we can relate the strength of the hydrogen emission to the amount of stars that are being formed in that galaxy. We can actually measure the change in the star formation rate or other properties of galaxies in that system. And so that'll help us understand why there might be a lot of galaxies in some systems and not a whole lot of galaxies in other systems. And in fact, Joel, who's on the call here, is our expert at this. So he's taking all of this data, putting it all together, and selecting the galaxies in these images. He's contrasting these various images to pick out which galaxies are probably at the distance of these structures, and then starting to look at he's basically counting up these types of galaxies and trying to understand what the distribution of those galaxies tells us about the structure formation itself.
It's quite clear. I mean, the way you explained it, looking at this contrasting these two images here, you can really see so many things are much clearer in the narrowband filter than with the others. Some stuff in the red circles and the first image, you just don't see anything, and then it just pops out. And the
Yeah,
second,
like the one that my cursor's over right here, this is a really good one. Like it's just there's effectively absolutely nothing in the K-band image, and then it's just bright and super bright in the narrowband image.
so these galaxies that we're looking at, they're so faint here that you're looking at. How are you able to determine the amount of stars there, let alone like determine the formation rate and all of that? I mean, it's so faint. How do you even see the stars there?
Yeah, we asked Joel for that.
Ah, Joel. Okay.
So the K-band so the K-band is at 2.1 microns, and the redshift, so basically the amount of times that the universe has expanded from the present day to this to the epoch in which these galaxies reside, is 2.5. And so you in order to measure the true emission, so the true wavelength of the emission of that light, you divide by 1 plus the redshift. So you're at 2.1 microns, you divide by 1 divided by 1 plus 2.5. And so it turns out that the actual light being emitted is roughly a 0.7 microns, 0.6, 0.7 microns. And so there's a very strong correlation between uh, light emitted at that wavelength and the stellar mass of a galaxy. And so you can basically, through modeling, it's a bit more complicated than that, but you can take that, what we call monochromatic flux density, or basically brightness in that band, and you can translate that into a certain stellar mass. So like Nima was showing plots with stellar mass on it, and so billion solar masses or 10 billion solar masses. That basically comes from measuring the amount of light, knowing the distance to each one of these objects, using some models, and then you get the stellar mass. And so from that, this contrast tells you the strength of the emission of hydrogen at a specific wavelength at 0.65 microns. And that you have assumptions and models that go into this, but can tell you the amount of stars being formed in a given galaxy, because basically as young stars form, they light up pockets of gas. Pockets of gas, it's usually hydrogen and helium and trace metal content. The electrons in the hydrogen atoms, they are ionized, so they extend out into the medium there, into the gaseous medium. Then they recombine with the protons and they emit hydrogen, this hydrogen excitation photons. And so you can basically count, like, I see 10 of these photons, that means 3 stars have formed, because we know that there has to be this amount of output of photons from these massive stars to cause this ionization effect, and then recombine and re-emit these hydrogen excitation lines. And so by the strength of that emission, you can get the amount of stars that are being formed. So you can get the stellar mass, you can get the amount of stars that are being formed just from these images alone, using some assumptions, some mathematics, some models.
Wow. Okay, that's an incredible explanation, and I think I followed all of it. And Joel is doing a lot of this work.
Yeah, so Joel's doing most of our selection, and then he's measuring the intrinsic luminosity, so the brightness intrinsically of these sources of the hydrogen emission, and then using that to construct basically counting up the number of galaxies at different amounts of star formation rates, and comparing that to other structures that that are selected by other means, or comparing the ones that are very galaxy deficient to the ones that are very galaxy rich to see if there's differences in the star formation processes. Because you would expect if the galaxies are having a hard time forming, that their star formation rates in general are quite low, because you just don't see them because you need stars to be able to see them in the image. And so we can test that assumption by doing the work that Joel's doing.
Joel, so how did you go about having this kind of role on the team? Did you already have the background experience and knowledge necessary to contribute this kind of expertise to the team to pull out the data that they're looking for, or did you start to learn this as you worked with the C3VO team?
Honestly, I had a background more in black holes and some in exoplanets. So I just learned as I went and I loved it.
Wonderful.
I was gonna say I joined the team last year, I believe in August or September, because I reached out through one of my professors at my college, and she knew Roy, and then Roy introduced me to the team, and so I've just been with him ever since.
A lot of times it's who you know. So Joel's professor was a graduate student in our PhD program at the Institute for Astronomy a while ago, and she's now a professor where he was a student. So, and she knew the field I worked on, so that's how we got hooked up. So, and he's totally different part of the country. We work virtually together, and actually our whole team does that. We have weekly virtual meetings with everyone in our team, and then individual meetings or smaller subgroup meetings on people working on specific projects.
Yeah, so I'll just say overall, the thrust of our of our astronomical census is very similar to the LATIS team, but we're doing observations specifically that are galaxy traced. So the LATIS team uses this gaseous medium, the intergalactic medium, to trace matter. We're using galaxies to trace matter. And so we also use like Keck Mossfire, Keck Deimos, GMOS, and Subaru to pick out the galaxies in these structures and to look at the effects, the co-evolution of the formation of the structures and the galaxies themselves. And so, as Nima said, these are complementary viewpoints because you can't always get all the galaxies. The systems that are some of them that are very gas rich don't have a lot of galaxies, but some of the systems that are gas poor also have a lot of galaxies. And so there's a contrast there, and it helps to look from a variety of different perspectives. And so the Hyperion proto-supercluster that Nima mentioned, this is a system that our group found 7 years ago, that was traced by galaxies, and it turns out it's also very, very well traced by gas. But there are some systems that are nearby that don't seem to have a lot of gas, or that gas is heated because they only see that gas if it's cold, so meaning less than 20,000 Fahrenheit. And so if gas is gravitationally heated, which it is in massive structures of galaxies, so like this SMAX system that we were looking at earlier, the gas is heated to several million Fahrenheit. And so in those systems, you wouldn't actually see the gas. There is a lot of gas there. In fact, the gas is the dominant baryonic component of the system, so by mass. But you wouldn't see it in this type of method. And so looking at a variety of different what we call tracers to find these systems is very helpful. And so this is the interface between the LATIS collaboration and the C3VO collaboration, is that we come focused on galaxies and we're just counting galaxies, and they come focused on counting the gas and looking at the gas distribution. And we meet in the middle and we try to figure out, well, okay, so why are some of the systems really, really rich in galaxies and poor in gas? And why are other systems really, really poor in galaxies but rich in gas? And so we've been taking these observations for quite some time, but we basically just started this collaboration because you can imagine it's very difficult to find these things to begin with. You're looking at things that are billions of times fainter than the night sky. You need lots of time on the telescope. You need very specialized equipment. And then you're looking over these areas that are the size of several full moons, where field of view of a telescope is not that, at least not the telescopes that we use. And so you have to build this up over a long period of time. And so it's taken us near a decade to build up the observations, the galaxies, actually a decade and a half to build up the observations of the galaxies to trace these structures. And it's taken the LATIS team around a decade to do the same for the gas content. And so and then we have to train everything on simulations. And so it's a very complicated endeavor. But we're starting to get there because these are some of the first looks of at these structures in the early universe. And we have the luxury of looking from a variety of different standpoints to be able to parse out some of the physics that's happening in those systems.
So even though you just started this particular collaboration, you've both teams individually, as you said, have been working on this for over a decade and a half. Have you come to any preliminary conclusions yet on how these galaxies transform into these massive structures? Anything that any insights that you feel comfortable sharing with us on that point yet?
Yeah, I'm happy to. I know we're getting close to the end of the session, but I'm happy to just do like a kind of quick overview. And there's a lot of our team members that aren't here tonight. Actually, we have a team of about 15 people all over the world. And I'll just give a shout out to a couple of them, some of which who were on the call earlier and some of which are visiting me here in Hilo and are now sleeping. But yeah, so the C3VO survey, this was built off of a couple of other surveys, most notably the VMOS Ultra Deep survey. Let me do an actual slideshow.
We love our acronyms.
Yeah, we have nested acronyms. So I think we've determined we're 3 nested acronyms. So we go C3VO, which is charting cluster construction with VOODS and NOIRLs. VOODS is VMOS Ultra Deep Survey, and VMOS is the visible. It used to be visible infrared multi-object spectrograph. Now just visible multi-object spectrograph. This was a instrument on the VLT telescopes, so the 4 8.3-meter telescopes that are also in Chile that are pictured on the top right there. And Nima mentioned, I think, 12-hour observations for their targets. For the targets that the galaxies that were observed in the VMOS Ultra Deep Survey, these were observed for 28 hours at a time. And so this is, a huge telescope collecting power that's about 60% more than Magellan. and an exposure time that's just insane. So the idea was to do basically the same thing as what LATIS is doing, except to go out a little bit further in distance, and to the resolution was worse, so we weren't able to do like the IgM tomography that they were able to do. But it's to go down to integrate, so to observe, so that we could see basically all the way the entire rainbow in the ultraviolet. And so we were able to pick up a bunch of different structures in this survey. You can see, like, so these are the references of the papers. So the first time that we were seeing things, this was more than a decade ago. And the C3VO observations were born out of this. So taking all of these Woods observations from other astronomical surveys that took place in these same fields, and then adding to it observations from Keck, Subaru, Hubble, James Webb, Gemini, and now Magellan. And so we have, lots of preliminary conclusions. The first thing we had to do was find these objects, and that took a very, very long time. And I'm sure Nima could talk for a while, and Drew Newman, who's the PI of the LATIS survey, could talk for a while. It is really hard to find these things. It takes you have to be very clever in your techniques. You have to have really exquisite data, and you have to train your analysis on simulations. And so it takes even to just figure out how to map these structures takes years and years and years of work. So in the new era of observations that we took, the first one that we found was this structure here. This is by Liu Shen, who's a postdoc at Texas A&M, who's visiting me here in Gila right now. And this is a system that's, again, about 2.5 billion million times the mass of the sun. And this is a similar system that's was observed when the universe was about 10% of its current age, by Ben Forrest, who's on the call earlier, who's since gone to bed since he's in Colorado. And in both of these systems, what we found was that the mass distribution of galaxies, so if you just count up the number of galaxies and you count up the number of stars, the mass of the stars in those galaxies, in these systems, if you compare that to areas where galaxies are not residing in these very massive structures, what you see is a shift. You see a shift to higher masses. And so the galaxies that are embedded in these structures, for some reason, they've been able to form more stars than the galaxies that are sitting outside of these structures. So this is an accelerated evolution. They've been accelerated in their stellar content. And this could be a variety of different reasons, but the two main culprits are the star formation has increased over time for reasons that we don't necessarily understand. So for whatever reason, increase in gas content, that gas has been compacted in some way, and so basically forced to form stars, that it's been interacted with, and so it basically fragments easier, and so it's easier to form stars. That's one pathway. Another pathway, which a student of that's working with Roy and myself, Finn Giddings, is working on, is looking at the interaction rate of galaxies. So basically, when galaxies collide, what happens? And he finds that galaxies interact roughly 3 or 4 times more in these types of systems than they do outside of these systems. And so galaxies are really interacting, stripping each other of gas, funneling gas towards the center of each other, and causing a star formation activity. And so in both of these systems, we see that. Ekta Shah, who's a postdoc working with us at UC Davis, this is a compilation of structures that she discovered in a different field, not one of the lattice fields, actually. This is a field called the Extended Chandra Deep Field South. And each one of these systems that's shown here, of these 6 systems, is more than, again, a million billion solar masses. So we have something like at least 50 of these structures that we found in our survey. And what ECTA found in these systems is that the fraction of galaxies that are undergoing active black hole activity. So basically, matter is accreting onto the black hole and it's shining very brightly in X-rays or in radio or in infrared light. It's almost 5 times the rate in these types of systems as it is outside of these systems. And so this is consistent with the previous picture of galaxies having lots of activity, building up mass very quickly, a gas getting funneled towards the center of these systems. And Denise Hung, who is a now science operations specialist at Gemini Observatory, Gemini North. She just put out a paper with 500 of these structures that we discovered in the survey, about 100 of which were known previously, but 400 are new. And so we're just at the very beginning of really trying to understand what these systems look like and what the galaxy content looks like. So that's we have tons of other results, but that's a broad brush look at what we've seen so far.
And I know we're running late, but I wanted to share a slide that sort of gives people an idea of how our thought process works in these kinds of studies. So team members have seen this, right? So I always like to think galaxies are and these clusters are very ethereal things to us, but you can look at a map of the United States and the top image here, the sort of yellow and brown one, is a map of population density. So darker areas have more people, more concentrated. And the bottom right map is how people vote. And they're clearly tied to each other. There's some correlation between them. Areas that are dark, that have higher population density, vote one way, and lower population densities tend to vote another way. But nothing tells you in this kind of correlation why. So you can think of one of these as the lattice maps where there's gas, we're tracing gas, and another one is our map of galaxies. And we want to see what's making things. We can also then look in more detail, or we can look in other colors. So here's lighting in the United States. And that's also correlated, not surprisingly, to population density. But you would probably find places that have low population density but high lighting. Why? You then ask yourself why. Maybe those are industrial areas. No one lives there, but there's big factories or something like that. Or similarly, you might find some outliers of places that have high population density but vote differently than other places. And even if you see these correlations, you can ask yourself, oh, is it that being high population density makes you vote one way or the other? And then you ask why. Or is it that people who want to vote one way or the other migrate to those places? So is it an effect of the environment? Or is it that some kinds of galaxies prefer to live in different kinds of environments? Or is it both? And so just like in sociology, often the answer is complicated. And so those are the kind of like ways that we're trying to analyze things. And even in things like galaxy interactions, you might say, oh, well, in cities, there's a lot more people, so they interact a lot more. But I grew up in New York, and the way you interact with people is you bump into them and you walk past them and say, flip them a bird or something. So it's a very short, quick interaction, and not a lot happens. But there's a lot of them. In other areas, in suburbs, you stand and chat. So you have more intense interactions over longer periods of time, but fewer of them. Which is more effective? How do they change you in different ways? So similarly, we have different physical processes that happen in different places, and we don't understand all of them and what happens to be more effective at making you form more stars or less stars, or making you form stars quickly or slower, or turn on black hole activity, or all this kind of stuff. And that's what we're trying to disentangle in the studies that we're doing in part.
Well, thank you, Roy. I think that was a great way to get us wrapped up here, and certainly gives us more to look forward to with observations with you and Joel and Brian and Finn and the rest of the C3VO team, and maybe even the LATIS team in the future. We certainly appreciate being able to shadow you all this evening. And in the chat, we got lots of thank yous for your work, and the people have learned a lot and are interested in where we can find. Yes, thank you so much, Rob. Again, another thank you for the session. Where can we find a latest paper that I can share with the registrants in the group? Or if you can just drop a link in the chat, that would be great.
Yeah, let me get one for you. 1 sec.
Thank you. Thank you so much.
I was gonna say for like papers in general, you do like ADS. There's a website that's like NASA and Harvard collaborated to it, and it just shows a bunch of most papers that everyone has written, and you just search by author.
They're all technical astronomy papers, though. So
Yeah, so I put one in the chat. This is by Drew Newman, who's the PI of the principal investigator of the LATIS survey. This is a paper from in the journal Nature, and so it's a bit more accessible. It's still pretty technical, but it's a bit more accessible in that it tries to tell a story a little bit. And this is about the systems that appear to be the types of systems that we're looking at that appear to be galaxy deficient, but very, very massive.
And I just threw a general link in there about our survey. There, it has a list of some of the papers we've written, and it talks a little bit about the science that we're doing and some of the results.
Perfect. Thank you. I'll make sure that everyone who attended today gets that. Thank you all so much, Joel, Roy, Brian, Nima, everyone. Thank you, the support staff at Las Campanas Observatory with the Magellan Telescope. Thank you all so much for all that you're doing to support these amazing teams, and we appreciate your support for Shadow the Scientist. We certainly look forward to joining you again in the future for further observations. In the meantime, for this evening, I hope that you all continue to have good weather and get some good data. Thank you so much.
Thank you, everybody.
Well, thanks,
Thank
everyone.
you.
Thanks.